Hey programmers, Alvin here. Right now I want to go over this max root to leaf path sum problem. Pretty wordy title. Let's take a look at what this problem asks us to do. So we're going to be taking in a binary tree as input, and what we want to do is really talk about the paths within this tree, in particular root to leaf paths. So just to review, we know that a binary tree typically for us has a single root, and you can identify the root by just looking at the topmost node, that is the node with no parent, right? And then also given this tree there are 3 leaves, right? A leaf is a node that has no children. So do bear in mind, right, a root has no parent, a leaf node has no children. Something like 11 and 3 in this picture, they're neither roots nor leaves, right? So it could be the case that a tree has many leaves, like this tree, right, has 3 leaves, but a tree for us typically only has a single root. And so what we want to do is consider all 3 of the different root to leaf paths, right? So you must start at the root and you must terminate at a leaf. So one of those paths would just be this one, right? 5, 11, 4. And what we want to do is consider its total sum. So just summing the values within the nodes along that path. If I do 5 plus 11 plus 4, that would give me a total sum of 20. So that's just one of the possibilities. If I look at another path, let's say this path of 5, 11, 2, 5 plus 11 plus 2 would give me 18. So that's another option. And the only other option is this final path from 5 to 1. If I do 5 plus 3 plus 1, that gives me a total sum of 9, right? And now among those 3 options, I want to choose the maximal path sum, right? So that would be a final answer of 20. So in the long run, we need to come up with some code that computes the maximal path sum from the root to any leaf. And that sounds like a pretty hard problem, right? How can we go about doing that one? Well, hopefully you notice some similar patterns, right, to problems we've done previously. So just by looking at the name of this problem, I'm reminded of a few different patterns, right? I can think of the tree sum problem, seems pretty related here. I can also think about like that min value problem where we had some minimization logic, except now I want to maximize something here. And so probably what I'll have to do in this one is combine some of my previous knowledge to come up with a pretty novel solution. But it's okay to rely heavily on our previous experiences, right? And so let's start with something classic. I think we're going to solve this one recursively. And in the grand scheme of things, typically for tree problems, that is, a recursive code is usually your best bet when it comes to like path finding things, right? And building paths and determining paths. And so we'll take a look at what we should have our base cases be if we're going to frame this one recursively. So they tell us that, all right, you need to consider paths, but not just any paths, right? You always want to end at a leaf node. So the leaf node is like the ending point. The leaf node is the base case. So my base case is going to be literally about a leaf node. And recall that that's a node with no children. So for example, let's say we had a node as input that had no children. Then what's the total sum of that leaf node? Well, it would just be its inner value, n, right? So kind of think about your base cases as if they're their own inputs, right? As a quick aside, right, so a totally separate scenario right now. Let's say I gave you a tree that contains only one node and its value was 42. And I asked you to, all right, tell me what's the maximum path sum of this tree? And this tree is very small, right? If you identify the root in this tree, it's just the 42 node, right? Because it has no parent. And I also ask you for the leaves. There's only one leaf here, and it's also the 42, right? Because it has no children, right? So the single node of 42 in this example is the root and the leaf, which means that the maximal path sum would just be 42. Cool. So I'm thinking about my base cases as if they're their own inputs. Nice. And what you'll probably recognize here is in this scenario, we're kind of considering a base case that is not about a null node, right? We will need at least a separate base case that checks if we have an actual leaf node. And that's very, very inherent and given in the problem, right? They say root to leaf path. Awesome. So if that's the case, I'm just going to locate all of my leaf nodes in this diagram. And I know that they're going to return the values within them. So just plugging those in, right? And now I can start reconstructing on my higher level solutions, right? So given this 11 node, what decision does this 11 node have to make to compute its answer, right? So let's root ourselves at this 11 node, and we have to consider our left and right values, right? And so if I root myself at 11, the 4 represents my max path sum through my left subtree, and the right-hand side 2 represents the max path sum through my right subtree. Since I want to maximize here, the key is to just choose between 4 and 2, right? I choose the bigger of them, right? So 4 is bigger than 2, so I must use the 4. And what I do is I take that 4 and I add my current value of 11 into it. And that gives me 15. And that would actually be the answer for this subtree. In other words, I can check for correctness right now. If I root myself at 11, I'm returning 15 to represent this path, right? I can either do 11 plus 4, which is 15, or I can do 11 plus 2, which is 13, right? And that 13 is smaller, so I won't prefer it here. Cool, so far, it seems like we're in good shape. Now let's take a look at another node we need to evaluate. Let's look at this 3 node. So it has a value on its right-hand side, right? It's receiving a 1 from its right child, but the left child doesn't exist, right? And if you want to be a little more explicit, we know that the left child, or 3.left, is going to be a null pointer, right? So I'll kind of plug that in here. And here's where we should work in possibly another base case. Sometimes it's very natural to just course correct as we go. And so for a null node, what should we return? Well, we know that whenever we have a null node, it should never contribute to our final answer. We can kind of just ignore it, I guess. But we want to make sure that it's compatible with the rest of our internal logic. So bear in mind in this problem, I want to take the maximum, right? Recall from our previous problem, right, the min value problem, we want to take the minimum. And so we made our null nodes return infinity, right? Because if I want to find the minimum and my null nodes return infinity by default, I know that infinity is never going to win a comparison, right? Because infinity is very large. And we just want to flip that logic over here, right? So because in the long run, I want to find the maximum, I'll make my base case for the null nodes return negative infinity, right? Because I know negative infinity is never going to win any contest where we compare things looking for the larger of the values, right? So for this null node, I'll plug in that negative infinity. And now I should be able to do the same business logic as before, right? So I'm rooting myself at the 3 node, and I can look at the results I get from my children, right? So between my 2 children, in my left path, I get a negative infinity, or in my right path, I get a 1. And I choose the maximum between them, right? 1 is bigger than negative infinity, so I should use the 1, right? And what I do with that 1 is I add my current value of 3 to it, so 3 plus 1 gives me 4, right? And that makes some sense because if I look at that small subtree rooted in 3, the biggest path from root to leaf or subroot to leaf would indeed be a 4. Nice. And now we have ourselves at the ultimate root over here. And I do that similar comparison, right? I check the bigger of my 2 children, so I'm going to keep the 15, but then I add myself to it, giving 20. Like we said before, this 20 logically represents this path of 5 plus 11 plus 4. Cool, so there we have it. And if we want to take a look at the complexity of this, seems nothing unusual. So we're going to have n as the number of nodes. We're going to have O of n runtime, because we're going to have to make a call, a recursive call that is, for every node within the tree. And if I think about any particular call we're going to make for a node, we're just going to do a comparison, right? I just choose the bigger of my 2 children. So we're not going to have any loops within our calls, I believe. Cool, so it just seems to be O of n time. And like we always say, space complexity is O of n just due to the call stack. Nice. So let's go ahead and code this one up. And it should feel like a combination of our previous tree sum problems, as well as some min value, max value logic.